Well, hey, greetings out there, everybody. This is welcome to another Takeo Tuesday. I'm John Barba with Takeo Comfort Solutions, joined by our chief presenter for the day, Mr. Rick Mayo out in Mesquite, Nevada. How you doing, Rick?
Very good, John. How are you?
I'm outstanding. And
Outstanding.
the backdrop here looks a little bit different. I'm actually in the factory in Cranston, Rhode Island, for only the second time in nearly 2 years. So it's good to have some sort of a return to normalcy, kind of, sorta, which is maybe the best we can hope for right now.
Yeah.
Thank you, everybody, for taking the time out to join us today. And this is going to be a really, really rocking good session on expansion tank sizing and considerations. And Rick's put together a really, really in-depth and detailed presentation for you to help you get some good information on expansion tank sizing and other considerations when it comes to getting your boilers set up properly. As always, I want to make sure that you guys are set up properly and know what you got to do. Take notes here. That's the thing you got to do. Make sure you have
Hey,
a
John.
notepad. Yes, sir.
Let me interrupt you just because on my end it says attendees are still on hold.
Attendees are still on hold. Well, no, we
Yeah.
started the session, so I'm hoping everybody can hear us. Guys, can you hear us out there?
Send us something, folks.
Send us a note. Go down to the chat section and type in a hi. Yep, Warren, you can hear us. Good.
Okay,
So
very good.
we
Sorry.
are live. There we go. No
My
problem.
apologies.
No problems. No problems. Since everybody can hear me, you guys know how to type in questions. That's good, because this is how you're going to do that. Please type in your questions as they occur to you during the presentation. We'll take a break every few slides to address a couple of them, and then at the end, anything that's left over we'll address, and we'll stay on as long as you guys need us to. We're happy to do that, guys and ladies. We're happy to do that for you. So questions are very, very important, because if it just left to our own devices, neither Rick nor I are particularly interesting people or engaging speakers. So we need your questions to help us out here. So please make sure you ask your questions. And also, please, if you would, make sure you have a pad of paper and a pencil handy, or a pen, and take notes. Write stuff down as we go along. That'll help you stay focused. Webinars are funny. We know that you're going to check the phone, maybe email, a text here or there, look at Facebook. It's easy to zone out a little bit. And then we become like the adults in Charlie Brown. The only thing you'll hear is wah, 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 wah. Right. And you'll miss a whole bunch. And we don't want that to happen. Now, of course, tomorrow at this time, you will receive an email from us with a link to the recording, as well as a certificate of participation that you can download. But you will have that recording to go over as many times as you want. So don't worry about missing anything. But taking notes is going to help you stay focused. And again, ask those questions. So without any further ado, I'm going to just hush my mouth and turn it over to Mr. Rick Mayo. Rick, take this show away, if you will.
Thank you, John. Appreciate it. I'm going to turn off a couple things here and push that over. And as long as you can see my start screen, I will begin. All right. So John's kind of give you a heads up on what we're talking about today. Let's just jump right into it. Types of expansion tanks. Here's one. This is a throwback. Anybody remember that? Because I personally don't remember these styles, but I got this information from Ronnie Falcon, our guy back in Fall River, and this is apparently this is the way they did it. Kind of unheard of now, but this is one old style of expansion tank. How many? Let's get a quick type back to us on how many people still see these style of tanks in residential applications. I know there's some old houses out there, but how many of them still have a horizontal plain tank in the rafters, so to speak? That'd be good to see if if those are still around, if you guys are still servicing those and still putting the little bleeder valves and sight glass and everything else on there. That'd be good to know. So along with that, we've got closed type expansion tanks with an actual bladder. We've got what's called a full acceptance here. Okay, that just means full acceptance means that the bladder inside the tank is as big as the inside of the tank. So if you were to ever fill it completely up, you wouldn't break or blow up the bladder. Okay. Now, on the other hand, with a partial acceptance, okay, full acceptance, partial acceptance, you could, if you grossly undersized the tank or had some things go wrong or wacky, you could fill this partial acceptance up to the point where you could tear, rip the bladder. Okay, so just showing you some cutaways. These pictures come from Fall River as well, kind of give us an idea of what we're doing now. Again, today's course is on residential stuff, and you'll see where that's going. But just generally, it's good to have an understanding of what kind of different expansion tanks are out there. Okay, again, this is a diaphragm style. These were the bladder style. This is a diaphragm style, okay, just like you could imagine there. And again, those will accept some expansion into the. Generally speaking, if somebody were to say, well, which side is which? Well, the bigger side is generally the side that'll have the air. You'll see why I say that here as we start looking at some principles. And the smaller side would be the one that has the fluid. Generally, this would be pushed all the way up against this, and then as the fluid expands, it would push down. We'll show you some cartoon examples of what that's going to look like later as well. As mentioned, today's session, we're just talking about our little residential stuff. You guys know where I'm going with that. There's our Tanko little tank that would give us a nice little package, okay, that we'll talk about in future classes. We'll do a little deep dive into some of our near boiler piping trim kits and some things like that. So anyway, so let's look at the anatomy of an expansion tank, okay? So we cut that away like this, and let's just break it down. Again, if we had a cutaway of one, which I didn't have a good picture of one, so I just drew this up. So this kind of helps you get an idea of what we got. First, we've got a deep drawn shell. Okay, it's just a steel shell, mild steel typically, that's made. There's some welding done on it. It's made to a particular size for a particular model number, et cetera. And you've seen lots of them out there. Okay. The tank connection, generally speaking, on residential applications is half-inch male thread, male iron pipe, and that's usually the only interface we have with it. We've got right around this edge right here. We'll typically have a spot to put a wrench on and tighten it up. Where this actually meets the tank is the least noble portion of an expansion tank. And that's not to say anything to degrade it or derate it or anything. It's just that most of you know that have been in this business and done any service work at all. When you see an expansion tank fail, it's normally right up here at this welding spot here. So that's why I say that's the least noble. And we'll talk about some of the ways these should be hung as well. So you'll see maybe extend the life expectancy at that point as well. So way back in the late 1890s or early 1890s, August Schrader had a company, and he came up with this thing called the Schrader valve. Okay, so that's been around a while. It's real similar. For those that don't know, that's real similar, probably almost exactly what you have on your automobile or your bicycle tire, hence the Schrader valve. So and of course, this side of the tank, I'll talk about this little black thing here in just a second, but this side of the tank is where the air's at, and it's captive, right? The air is not going anywhere. As long as the Schrader valve's not leaking, and as long as we don't have any leaks here where the seals are, this diaphragm actually attaches, and the diaphragm sound, that air is going to stay captivated inside that tank. So that's our captive air side. Now, if we start actually filling the system up as the fluid expands when it's heated, right, then of course that's what happens to this EPDM diaphragm. It starts pushing back out there. Okay, that EPDM diaphragm moves as the fluid moves. Okay, and I'm going to say this. It seems like really simple, but I want you to imagine that as the fluid expands, how it moves on this side, it's taking up space here. Before it had all this room, and now it's having that room displaced. So, and I'm saying that for a reason. Just hold on to that. As John said, it'd be good to take notes, because once we get into looking at what happens, you'll get a better idea of what happens. And I'll actually give you some examples of what's happening on this side as we see the expansion occur. So Location, location, location. And we say that about a lot of things, and because it's important in our industry, a lot of times when we stick something somewhere, sometimes we get it wrong. And you know what? When we're talking about the expansion tank location, we have to hammer this home. And this has been hammered home for, I don't know, maybe 60 years now. But it's still, we see it being done wrong, and so we do have to talk about the expansion tank location. So let's take this little area here. This is just one of our little home drawings that we teach off of a lot, but let's drill in and focus on this area right here. Now, we're going to talk about, this, again, this would be a system circulator pumping away from where the expansion tank meets, etc. But let's call this out, right? Let's call it for what it is. Right where the expansion tank actually meets the system is the point of no pressure change. Okay, and we'll drill into that a little bit. So if it, we're not gonna, go real deep, but we'll do a quick review on what that means to us. A very important part of what we do in the closed loop hydronic business. Okay, another thing that we don't talk about a lot is from the point of no pressure change to the system circulator. That's actually critical. Just like a lot of times, this pipe here, a nice straight piece of pipe before you enter the inlet side of a circulator is very important. We want that to be as long as possible. We'll give you some minimums, and they kind of go hand in hand with the minimums or the maximum distance that we want from this as well. We'd like to say about 12 pipe diameters, okay? So if I get a nice long piece of pipe here, I don't want it to be too long when it's associated with the point of no pressure change. Okay, we want a maximum of about 12 pipe diameters from that point. And the reason is, if we have flow going across this line, we have some additional pressure drop here from this point to this point. We just, don't freak out about it. Maybe make a note, 12 pipe diameters, but just understand the concept, right? Concepts are easier to walk home with. Get that system pump fairly close to where that expansion tank meets the system. Okay, and that is something that's usually not talked about that often, but it is an important point. Okay, so let's focus on the point of no pressure change. A little review for those who have seen these presentations before, but we say, look, we call it the point of no pressure change. However, there are three things that can change the pressure at that location. Again, if I add or remove water from the tank, that would mean that the fluid side of this if I start adding fluid, then I know I'm going to change that pressure gauge. Okay, so we know that will take place. Add or remove water from that side of the tank. The other side of the coin is if I add or remove air from the Schrader valve, right, from that portion of the tank, I could change the pressure on this gauge. I will say this real quickly. The only reason I have this little cartoon here is because I don't see a gauge right here at the most critical point. Okay. Again, some of you have heard me kind of get on my soapbox there. Realistically, this is the only place you ever want to see what the pressure of the system is. Doesn't matter what the pressure is of the boilers nowadays. These small, relatively speaking, no fluid quantity boilers. It doesn't really matter what the pressure is. We want to know what the temperature is, but we don't really need the traditional tridicator, thoroaltimeter type gauges there anymore. That was kind of old code stuff. Now, again, your local code always prevails, and they might still be making you put them on there, but it's very important to see what the pressure is right here at the point of no pressure change. Thirdly, on this is the system fluid expansion. Of course, once the fluid inside this system starts heating up and expanding, that will change that pressure gauge for sure. So again, why do we call it the point of no pressure change? That's because of this last statement down here, or a question actually. Can the system circulator, like this in this case, change the pressure at this point right here or here in this case? So, and the answer is no. Okay, real simply, without going to more of an explanation, look at it this way. If I were to change this pressure in a completely closed loop system with no air in it, if I were to make this go up with a pump or anything, what would have to happen is water would have to come down this pipe slightly in order to change that gauge. And most of you can nod your head, yes, it would have to somewhat slightly move downward in order to increase the pressure here. And if it were to do that, the question is, where would it come from? Okay, remember, it's a completely closed system. It's completely full of fluid. We can't compress the fluid, we can't tear it apart, etc. That way, think about the fluid in the system as a bunch of links in a bicycle chain. You would have to add links to the chain to get the chain to all of a sudden droop down into this area and create higher pressure. So anyway, again, we normally elaborate on this a little bit more, but this is a quick review since we're talking about location of the expansion tank. Okay. Any questions so far, John? I guess not.
There we go. No,
Silence.
I'm sorry. I had to get to my unmute button. None to speak
That's
of at this point.
okay. Thank you, sir. All right. So one thing, little tips and tricks that I've learned throughout the years. Always check the PSI of the factory charge at the Schrader valve location. Okay, prior to installing the tank. Okay, that's just, we're talking about something when you pull this thing out of the box, the shipping crate or whatever it is. Okay, everything I'm talking about applies to commercial tanks as well, for the most part. Okay, so before you do anything as far as hooking up the tank, you know, uh, starting before you start twisting anything on this thread, there's a couple of things I want you to consider, and that's what these next little bullets are. Okay, so don't trust a factory precharge. Get your nice little AccuGauge out and check it. See what it is. There's two things we want to look at. If we're going to stay with the factory setting, make sure it's still what it's supposed to be. If we need to change it, like we often do, then we want to make sure it gets changed to the proper pressure on the site. And it's ever so important to remember it has to happen when we're talking about changing the pressure or checking or doing anything. You cannot have any pressure up on this nipple. So you have to know that. That's why I'm telling you, on new jobs or even service jobs where you're changing the expansion tank out, always check this and confirm it before you actually screw this or into anything or anything onto that nipple. The other thing we have to remember, some of you know that I used to live up in Alaska. I came up in the trade up there. I worked as a wholesaler up there. And one of the things that people forget to do, they might pull an expansion tank out of their truck at -30 and bring it in and hook it right up. Well, we kind of want to get that thing a little bit acclimated, okay? So whatever the temperature inside the mechanical room where you're working, just wait long enough so that the tank is the same temperature. It's just a good practice, okay? So acclimate that thing. And we're going to show you how to do this calculation. We'll talk about what calculation you should use to ensure you have the right number on the captive air side of this. Okay. Now, and as mentioned, if I have a good sized tank, you better have a suitable size compressor to do this job. You don't want to be using a bicycle pump on a larger tank. You will be there forever. You will get your aerobic and your upper arm and chest exercise if you don't. Okay, so believe me, I've embarrassed myself here. So get an appropriate size compressor for the job. Okay.
Hey, Rick, when you
Yeah.
talk about letting that tank acclimate, I just wanted to point out any good New England Patriots fan knows about the ideal gas law, which is basically what you're talking about. And I'll say it here and I'll say it now, not a darn thing happened to those footballs. It was 5 years ago, but we can let it go, just so you
Oh,
know.
I see. Yeah.
Take it away. I'm shutting up now.
I love it. I love it. I know where you're going with that one. All right. Very good. So mounting. Okay. Well, just think of verticals, folks. There was a time, and I even had a copy of one of the major expansion tank manufacturers in the residential world. Was showing it basically you could put it in any direction you wanted to, but there were some, empirical data coming back that said, we need to change this up, and they actually changed their installation booklet to just say, look, mount it vertical, okay? Connection at the top, kind of like we're showing in most our drawings. Sometimes, there's just not room on the drawing and it's shown wrong. But you know what? The way we show it in a drawing is real likelihood of how it's going to be installed. So, as somebody who does drawings or used to quite a bit, and I do some for Tacos now, but I try to draw it when it's right. And again, don't get me wrong, I've made some mistakes. So just remember vertical and top connection. This will keep you out of trouble. Now, again, specifically, I'm talking about these little residential tanks. Okay, some of the tanks you get from us, you have one connection, and you're just going to connect it right there, and that's suitable as far as Taco is concerned. Okay. Um, here's something to think about, as the little note says. So most people think that when we start doing expansion tank calculations, it's all about the expanded fluid. Okay. Well, it is, because that's why we have expansion tanks. We know that as we heat fluid up, it expands, it moves, it grows, so to speak. But once you really start looking at the calculation itself, and you're better grounded in the concepts that are at hand, you actually can change your thought pattern. You can say, you know what, it's actually more about the airspace that's needed to accept that expanded fluid than it is about the expanded fluid itself. Okay, so get me on that. So I've already said this. It is critical for what the tank's air volume is. And it's funny how we do air volume, and in a lot of other industries, when we talk about air volume, we talk about it in a certain increment or a certain unit. But when we get into expansion tanks, we change that because of another concept that we use, and that's handling fluid. So we're in the fluid handling business, believe it or not. Okay. Anybody ever heard of Robert Boyle? Okay, he has a lot to do with this, or at least as a pioneer in what we're talking about. Don't get me wrong. I'm not going to throw a bunch of crazy stuff at you that's not easy to understand. I'm trying to conceptualize everything that I've read about, and it doesn't mean I know everything. It just means that I've tried to grab some of this stuff and just put it in simple terms. Again, I can't teach it until I somewhat get my arms around it, and some of this stuff starts out, like, oh man, this is a snooze. But anyway, just saying, I'll try not to completely bore you to death here, and you could still learn about something about Robert Boyle anyway. So how much should the pressure change? Going from a static condition, that's when you first set the thing up and no powers, you're just done your purge, you've done your fill, all that stuff. And before that system heats up to the point where it's running at a design load condition. Okay. So how much should the pressure change? The cool thing about, sitting through a session like this and having a better understanding is that you're in charge of that. You are in charge. You get to decide how much that pressure is going to change merely by sizing the tank more appropriately. Okay. So anyway, let's talk about air volume, since I've already kind of told you that's actually more important. We need the ability to receive that expanded fluid. So it's all about air volume. And in our world, like I said, in other industries, when we talk about air, like John, when we do a heat loss calculation, we do the infiltration portion of that, we're always talking about what? Cubic feet, right? Cubic feet. So, but when we get into expansion tanks, we take that back to another increment, another way of reading. So because we're dealing with tanks and fluid handling, we go back to US gallons. So we need to know, and some of you know what this number is already. Okay, if I have a cubic foot of air, how many US gallons are in that cubic foot? We use this, anybody has anything to do with, pool heating or spa heating, or any calculations for the raising fluid temperature in an open atmosphere kind of thing, you already know this number. Okay, but here's a little thing that just tells you. So for every cubic foot we have a 7.48. Just say, if you want a simple number to remember, 7.5 gallons. 7.5 is going to be approximately 1 cubic foot. Okay, this is linear. Okay, if we take it up to 10, it's 74.81, just to show you that relationship. So again, we got to switch everything to gallons. That's why you'll see the size of the tank in gallons, right? So here's looks like some kind of royal figure or something, but I think that's just the way they dressed back then. And John, these guys got to wear wigs, and they weren't, criticized or ridiculed for it either. But anyway, let's read this little quotation. The
Wait a minute, wait a
volume of
minute, wait a minute, wait a minute. Why are you referring to me like that? Yeah, I mean,
I
I
had
still
to.
have a little left, okay?
Yeah, I got a little left, but I just I take the shears to it frequently. So the volume of gas at a constant temperature varies inversely with the pressure exerted on it. Okay, folks, that's an old rendering of Robert Boyle. We'll put him off to the side here, and let's look at a different way of viewing what he's talking about there. So here, down here on the x-axis, we have volume. Here on the y-axis, we have pressure. And this is a little scale that kind of gives you an idea what happens, okay? So if you see something that says inverse as a root word, you know you're going to flip-flop. You're going to be the opposite of. So in this case, let's throw some lines at this. If I had an air volume, they're saying gases, right? Gas, but let's just talk about air. And if it was at a 40, right, 40%, and somehow or another I was able to squish that down to 20%, look what happens to the pressure. At 40, I'm about 35. I come up here, I'm going to be at double that at 70. Okay, so there's the relationship. So as this point here goes down this way, back down to this point, you will ride between these two numbers inversely. Okay, so that's what happens. So think about an expansion tank. As I start expanding the fluid on the other side of that EPDM diaphragm, it starts to compress the air on the other side. Okay, what's going to happen? Can we predict? Right? Yes, we can, and that's why there's these calculations that are as long as my arm. I'm not going to get into those calculations today, other than to just show you that it can be a headache. But understand this relationship. As we start squeezing things down, things change. I've got a couple other representations here, but before I do that, this guy kind of caught my eye for some reason. He kind of reminded me of somebody that I used to uh, recognize anyway. So there was a similarity there. So I'm going to give you a hint real quick. What if I put a guitar on this fellow right here? And not just a guitar, but a very special guitar for those who might get it. And I want somebody out there that knows where I'm going here to give me an idea who I'm talking about. And I'll give you a big hint, and I'll put him right over here. You fill that in and tell me who that reminded me of when I saw a picture of Robert Boyle. Robert Boyle and Boyle's law. The volume of gas at a constant temperature varies inversely with the pressure exerted on it. Here's a couple more pictures to drive that home, this whole thing about Boyle's law, right? So this looks like fluid with bubbles in it. It's not. It's a gas. Let's just call it air, okay? So I'm at a 4. I'm at a 1 on my pressure, and I'm at a steady temperature. Now, remember, part of that comment was that this is at a fixed temperature. This, as long as the temperature stays put, this is the result that we'll get. We know that as we increase the temperature in something, things are going to change. That's another attribute, and that could get more into some of these perfect gas laws and things like that. Again, I'm in over my head once I start talking about that, and even to this to some extent, right? So let's show this in a representation of taking it from a 4 down to a 2 based on what we know about Boyle's law. We already know that pressure gauge is going to go from a 1 to a 2. If we cut this down in half, then this has to increase by doubling. Okay, so a couple good things from Encyclopedia Britannica there. So anyway, hope that helps kind of get that to gel inside your mind. Again, it's all about concepts. Okay. Let's take this a little further and show you what happens as fluid starts expanding. Again, when you pull the tank out and you have 12 psi on a static condition and you have 12 psi here, nothing's entering the tank. Okay. But as the fluid expands, what happens to this pressure and what happens to this pressure? So again, with some calculations and making some predictions here, we're doing something that kind of gives us an idea what's happening. Okay, if I see this change, fluid coming in to this portion of the tank, so that I saw an increase in pressure, I would get approximately an 8% increase from the number 12. Okay, so again, this is not to scale. Don't kill me on this. This is just a my rendering of what this would look like inside the tank. Okay, again, as the fluid increases, comes in here, you're seeing this pressure raise. You're seeing the result of it in a percentage. That's all I'm doing. For the sake of time, I'm going to keep just showing you what happens with a 25% increase. Okay, what it would look like with a 33% increase. And finally, notice this just keeps moving, right? And 17 psi to 17 psi have equilibrium here, right? And that's what's happening when you see your gauge change within the system. Yes, the fluid's expanding, it's coming in here, but we're getting an increase. We never get to see a gauge right here, nor would we ever want to. You don't really need to, other than a quick little press on your little your accu gauge that could tell you what it is. But again, when this is happening, when the system's running, is not the time to be playing with a Schrader valve. Okay, there's really only one time, and that's when the tank is completely disconnected from the system. Okay, any questions so far, John? Okay, I know John's probably turning his mic off, so I'll say that there's
I'm back
no
on.
question.
There we go. There we go. Super important that the pressure must be corrected to absolute for Boyle's law ratios to work, says Warren Juergens.
Yes.
And we got some Brian Mays and some Jimmy Pages.
Whoever said Brian May got it. He gets, whatever prize we're giving away.
All right, we have winners for Richard and Bill. Got it. Very good. Very good.
Thank you. Appreciate it. Yes, everything that when we get into expansion tanks, we're talking absolute. And we're going to be teaching on that when we get into some understanding of the net suction pressure that's needed on these new ECMs, these bigger VR ECMs. It's important with every circulator, but when we start talking about wet rotor circulators, it's very important to not have the fluid boil inside the can being the portion of the wet rotor assembly. That's even more important in those smaller applications than it is about getting little pellets in our impeller holes, tearing things up. So anyway, we'll save that for another teaching. Okay, how important that is. Let's talk about the actual sizing of an expansion tank. Everybody's seen little things like this. This comes from our friends there in Rhode Island as well. And there's some things that are just kind of give you an idea. Hey, if you got this many BTUs, and you've got this kind of heat emitter, then this has worked, and it's been out there just based on, again, on empirical information, empirical, I mean. And you know what? It'll be out there and it'll work for the most part. My goal here is just to say there's more to the story, and it's better to have an understanding. And there's different ways to size things out there at this point in time. So anyway, expansion tank sizing. Let's go ahead and get this from the full-blown commercial stuff to something that kind of what we're talking about. Most of the software, including some of the information that's back behind the wall in Taco software, will have real long calculations like this. Again, I'm not going to bore you with this. Sometimes it sounds interesting. A lot of times, most people think it's just a headache. And again, this is the type of calculation that you would do that's based on a bunch of different um, variables that are out there. Again, we've got atmospheric pressure to deal with, as was mentioned by one of the people watching, etc. So we've got this thing where we're going to add pressure, take pressure away, and things like that. But let's go ahead and simplify things a little more. Okay. Since we're talking back to residential stuff, and most people on this presentation, I might be geared toward that. You folks realize that on our Takeo Tuesdays, we have a session like this that's geared more toward the wholesale or the residential type people, and then we'll have another one that's geared specifically for the commercial folks as well. So one thing that's important, this list I'm about to give you applies to both commercial and residential. We need to know this information one way or another in order to size the tank more effectively. Okay, so number one, and very important, and number one typically is the hardest thing to achieve a lot of times, and only because people do a lot of guessing. Okay, they do a lot of guesswork, but we need to know how much fluid is in the actual system. Again, I'll point it out that we don't care what the expansion tank holds. We just care what's in the system itself. That's the pipe, that's the valves, that's the fittings, that sort of thing. The boilers, the air separators, all that good stuff. So anything that's going to be full of fluid under a static condition, okay? Um, and we need to know something about that fluid. We need to know, whether it's mixed with anything like propylene glycol, or is it just good old H2O? Okay. We need to know what the minimum and maximum operating pressures are in PSIG. Okay. Minimum and maximum operating temperatures. Okay. We need to know what that is as well. And the relief valve rating. Now, some people will look at this relief valve rating and actually size the relief valve based on some components within the system. Well, normally in a residential application, the number one thing we're worried about is that boiler. And most residential boilers nowadays will have a 30-pound relief valve. So we're going to generalize based on a 30-pound relief valve. But again, we need to know this information. We need to know what that relief valve is. This will help us when it comes to figuring out what that maximum operating pressure up here is going to be. Okay. Again, a system static pressure. Again, we need to know how big the building is in height, because that will change, and it'll have to do with that calculation that we do back here on the expansion tank on the fill, the initial static fill pressure that we put on the system. Okay. And in some cases, a lot of cases, actually, this matters, but some software programs don't ask you this. Okay, I got one thrown in here, like Takeo's, which if I have time, I'll show you real quick. I'll show you at least an example of it. It's going to ask you whether your system copper or whether your system is steel, because there's different expansion. Coefficient of expansion of these two materials are slightly different. A copper expands more than steel does, and it will have you or give you the ability for a slightly smaller expansion tank. Okay. PEX, on the other hand, I know this firsthand. In the house, I'm not living there anymore. John told you I live in Mesquite, Nevada now, and I've got a good old heat pump sitting out there. But when I was in just outside of Salt Lake in Sandy, Utah, I had a full-blown hydronic radiant floor system that had a bunch of PEX in it. Okay, and I literally, one time I was doing one of the things that we were talking about. I was double checking what my air side pressure was. So I had a valve here, kind of like this is a little check valve assembly that we give you with this kit. So I spun my tank off, and I checked the pressure, filled it, made sure it was back up to 15 pounds where I was running my particular system, and put it back on there, tightened it down. Forgot to open the valve, right? And didn't know it, didn't even know at all, didn't see the gauge change that much, etc. So I know for a fact that the expansion of my fluid was being absorbed in the plastic pipe that was exposed. Now this plastic pipe wasn't embedded in concrete or anything like that. It was all open to atmosphere. It was one of those remodel type projects. So John knows where I'm going with that. But I guarantee you the type of material you have has an impact on the required size of the expansion tank. Anyway, just a heads up. So part of your handouts here, you'll see this little logo down here if it was part of your handouts. And I encourage you to grab those before we're finished. We'll give you a little time during questions. You can download those, or if you haven't grabbed them already. Okay, this is just a little handout I put together. We use this in domestic hot water sizing, but again, all it's telling us is what is the fluid volume of pipe in lineal footage. Okay. So what I'm getting at is you have to go to lookup tables of some sort. You can get it from us. You can get it from third party. You can look it up online. The people that make product will tell you how much volume is in all of their stuff, you know. So you have the ability. Remember I said the number one thing we need is the total fluid volume, and that's usually the hardest number to come up with. The other stuff, it kind of comes pretty easy. Anyway, don't add for the expansion tank. I said that already. So let's look at fluid densities. I'm getting this from our good old folks at Dow Chemical. And again, whatever brand glycol you folks use, this is where this came from. So I'm not leaning on them any more than this is the same chart I've used for 20 some odd years. So anyway, let's look at the density because it's one way of determining some things. So we have to solve for the density. Normally we'll take this and we'll divide that out, right? Let's get a number to start with because there's a temperature associated and a percentage of mixture of the glycol, in this case, propylene glycol. So 63.27 is how much that would physically weigh for a cubic foot of that product. So we use that density. We can break it down into a gallon, or we can just use a multiplier, or in this case, a divider right off of that number, okay? 144 is based on the units that we're using. Everything that we convert things to is in PSI, in this case, G, and we will base that on a cubic foot. So how many 1 inch, 1 foot, 1 by 1 foot columns are in a cubic foot? It's 144. That's why we use that constant for that. Okay. That if we do that math, that gives us this number. You folks taking notes, write that number down, and we'll show you how it plays into what we're doing later. 0.4394. Okay. So now we want to come up with that fill or operating pressure calculation. This is again how we know what that tank should have in the air side prior to hooking it up to the system. Okay, so we're solving for the actual fill pressure. Okay, it's based on looking at the height. Okay, in a vertical structure, we've got pipe, valves, and fittings that are going up vertically. Then we have that column weight coming back down. Good old gravity, things that you learned a long time ago. The good old conversion number that we use is 2.31 most of the time. I'm just showing this a little different just for the sake of variety. Okay. Fluid density divided by 144, and that's the weight as I showed you on that chart there. And then we're going to add, that's a plus sign, we're going to add 4 or 5 pounds, and I'll show you why here in just a second once we break this down for you. Okay. So minimum or operating pressure calculation, I'm showing you here. What we're talking about is where the expansion tank meets the system, in this case, showing you right there. I'm going to measure from there up to the highest portion of the system that has a heat emitter on it. In this case, it kind of looks like a panel radiator or a towel bar or whatever. Call it whatever you want. But we need to know 19 and 19 is 8. Excuse me. 9 and 9 is 18 plus 2. There we go. Plus 5. We got 25. Okay. 25 foot is what we're going to use in this calculation. We're going to divide that by 2.31. That'll break that down and give us what the pressure will be right here. Okay, and we're just making sure we've got enough to do the job as far as the next thing I'm going to show you. Okay, in this case, we're going to take that same 25 instead of dividing it by 2.31, we can times it by that multiplier we showed you that comes out of the density. Okay, 0.4394. Look, it's virtually the same number. If I took this number that would just be for water and round it up, then I'm getting real close to what my glycol mixture would have been at that specific temperature that I showed you. Again, there is a relationship on the temperature and the mix volume there. So let's see, why do we want to add that 4 or 5 pounds, well, I put a little air vent up here at the top. And if I want this to be something above 0, then I need to add, okay? And I want it to be higher pressure so I can push the air out. This is showing you a high capacity air vent like our 4900 series, a very high end, very nice air separator for those who don't know. This, in this case, it's just the air vent portion of a 4900 air scrubber. Okay, so let's look at that 4 or 5 pounds. What's that do for us? If I was going to use this number and I added 4, well, that tells me what I'm going to put on that tank. Now, I like 15 pounds. I said 15 pounds before. I liked it because when I pulled in my garage back up at my house in Salt Lake, I could look right at that gauge, and along that 30-pound gauge was right smack vertical like this. I know I was at 15 pounds, and I'd see that move a little bit back and forth as the system would heat up and cool down. So again, uh, what we want to do is have a little more control of how much that gauge moves, and that has to do. Very important part of this session is understanding of size of the tank. We can control how much that needle moves. Okay. Anyway, so maximum pressure calculation. Okay, has to do with the relief valve on the boiler here. Now, in this particular design I'm showing you, I am doing what's right, and I'm pumping away from the point of no pressure change. But there's jobs you folks are going to get into where somebody piped it wrong. Maybe you're out on a service job and you're pumping into the point of no pressure change. Okay, this is where this maximum pressure calculation applies even more. So be careful. Understand that if I'm doing it right, this doesn't apply that much, but it's nice to have an understanding of when it does, and that's what I'll just give you that right now. Okay, so if this was a 30-pound relief valve, I tend to want to never get approaching 30 pounds because these tend to weep, they tend to leak. If you got glycol in there, you're losing an expensive thing, it's leaking out. You got makeup that's going to dilute your mix, et cetera, et cetera. So there's things to think about there. So 30 psi, I'm just going to use a 5-pound reduction. That's fairly typical of what I've seen in my experience. Other people have taught me that down the, as I've gone down the road and listened to different people teaching this, that it's, again, 4 or 5. Some people use a percentage like 10%. Well, 10% would only be 3 pounds. So I'm going to go ahead and just get it back to a simple number. I take 5 off of 30 and I'm going to have 25 pounds. Okay. Here's my 30-pound gauge though, right? And I'm pegging that thing out. So I'm emphasizing that for a reason. Okay. So if 25 is my maximum pressure calculation, right, then let's rethink that maximum pressure calculation, because a lot of people would use that in the number for putting into the software. We'll give you an example here in just a minute, but I want you to think about that. If I go back again, do I really want that gauge pegged out like that for a design condition? Do you want to walk into the mechanical room during a design condition and see the pressure gauge only 5 pounds away from where your relief valve is going to pop? The reason I'm saying it like that is that's the way I want you to think about it. Okay. When you're coming up with a maximum pressure calculation, I want you to reconsider some things here. It purely has to do with the sizing of this expansion tank. Okay. There's that same picture we looked at before. I want you to focus two things: where the gauge actually goes, and do you want to see that in the mechanical room during a design condition? So that's purely why I'm showing you this picture again, where the gauge belongs, so it can be real at the point of no pressure change. And do you really want it to move that much? That would be probably a better way of saying it. Okay. So maximum head of circulator calculation, we said 25. Let's look at minus 15 for the operating pressure. We already told you that, I like to see these things at 15 psi just because it's easy to look at the gauge. Again, 12. If you like 12, that's fine too. Whatever it is, you're going to minus that off of that maximum. And the result is going to give you an idea of how much we should allow the circulator to add to the system when it's pumping into the point of no pressure change, which is really not what we want to do, but we will see it, Pete. We still see people doing it, etc. It might be just set up that you're going to use, like John has talked about, hey folks, if you must do that, like they used to come packaged, those are flat curve circulators. They don't add a lot of pressure, so we're not really as concerned with this. But this is just a way of being assured that you're not going to pop that relief valve with the pump coming on and off. Okay, so this is simple. Again, seminar land, we use nice round numbers. 10 psi, we take that divided by 2.31. We're just saying make sure that circulator doesn't have the ability of doing 23 feet of differential pressure to the system, and you'll never have to worry about popping this relief valve if it was piped incorrectly, like sometimes they still are. Okay, any questions, clarifications for now, John?
We had one, Rick. It was from Francisco. Could you please further explain why the 4 to 5 pounds additional pressure for the air vent?
Sure. If we were just sitting here at, like, 0 psi or maybe only 1, we're not going to do as good a job as getting bubbles of air that come up here out of this air vent. Okay, if I get a little higher pressure, that 4 or 5 additional psi, we just want that to be at the top. It does two things for us. It helps us get the air out better, and it also gives us the ability for the circulator, when it's running, to have a differential pressure that it's adding to the fluid, the mechanical energy that it's adding, and it induces flow better when we have that higher pressure up there. So hopefully that answered that question. John, feel free to add to that whatever you want.
Nope, I think you covered it beautifully. Here's another one. If the terminal unit manufacturer has a minimum pressure, do you add that too?
I've not seen the terminal unit have a minimum. I would just make sure that we meet that, though. It's, as long as in this case, we were running that at 15 pounds. When we go up our vertical, we have to drop that. Remember we did that division by 2.31 to see what we would be at the terminal. But I've not seen a minimum, so I can't speak to that. I just make sure that you're higher than that. I don't think you need to add it.
Gotcha.
Okay.
Carry on.
Okay. So expansion tank sizing, okay? We're just going to make it easy. We're not going to go into crazy calculations or anything for you because, again, we have lots of calculators online. Taco's got a nice one. Their online wizard that we use. The commercial people use this more than the residential people typically do, but it's a nice little wizard that you can go on and run some numbers just to get an idea of what you can do with it. But there's other things out there as well. I'll just show you real quick how to get to ours. Okay, you just pull up tacocomfort.com. You go over here to the selections tools and you'll click on that. When you click on that, you'll get this nice little screen that comes up over here. You see where it says expansion tanks. You click on that again, and then all of a sudden you're in like Flint. Okay, you got to tell it how much, what units you're using. Remember the question about fluid, what kind of fluid is it? Here's that one question on copper or steel, and you start filling in the blanks. What's your total? This is number one. How many gallons of that fluid is? What's your minimum of initial fill and operating temperatures? And there's your range right here. What's your maximum design temperature? That's the one I want you to be careful of. Okay, if you take this to the max and you've got a real sharp pencil on your fluid volume, guess what? You're going to be operating very close to that edge of that relief valve. So again, I'm pointing out the fact that this number you should give some more consideration to, and basically what I'm getting you to try to do is oversize your expansion tank a little more. Okay, again, a lot of times we already do that just by nature. So this is one of those things that's not a problem, and I'll finish up with that, right? So minimum initial fill or operating pressure, minimum and maximum. So you got max temperature, max of minimum, and maximum pressures as well. So anyway, I got that temperature flip-flop there. So anyway, everything that I put on that list is applicable. Okay. And then we put that in there, we click on search, and it brings up a bunch of cool things. Now, again, we're not going to go into that. I can see I don't have that much time. There's some third party stuff out there. Here's one that I used years and years ago, 20 years ago, that takes into consideration both sides of the system. There's some things out there like that. That you can find. Siggy's got a nice one as well. He does some neat stuff on his software, and there's others. Okay, plenty of people out there got something. Okay, so I'm not going to show you the calculation or anything, but what I did take the time to do is put this little chart together for you. And this is a quick reference chart. It's nothing more than that. It'll tend to oversize your tank for you, and you'll see that that's not an issue. It's based on some initial fill temperatures and some other things. Okay. We'll take our volume of gallons and just round it up in nice round numbers here. Again, this is real simple. I take a system that had 50 gallons in it and bring it over here to what the difference between my initial fill and whatever maximum operating temperature I'm going to be. In this case, if I were using these two numbers, I would use the 140 column. In my example, I'm going to only have 100. I'll be in the 100 column. Okay. So what I'm looking for are these two numbers right here. One's dark blue, one's light blue. Of course, dark blue is our expansion volume of the fluid. This is how much the fluid's going to expand in gallons. Okay. Notice it's a relatively small number. Okay. When we get into the TV, that's my tank volume down here, right? That's my tank volume. And that needs to be substantially bigger than the fluid. I led you and showed you what that's all about. So the tank, expansion tanks are sized based on the air volume more than the fluid volume. Okay. Hopefully you can get your arms around that, carry it home. Okay. Some other things down here, your initial operating pressure is 12. Maximum, notice I only let it go up 5 pounds. I didn't take it all the way to 25 pounds, right? So if I did, it would make the tank smaller, okay? But what I want is the reality. When I walk into a mechanical room and I see a design condition, I really don't want to see that gauge pegged out. That's my opinion. You do anything you want with that, okay? So understand that. Here's our propylene glycol uh, uh, multiplier that we would use, because again, when we get into glycols, they expand differently than water, and we have to count for that. And so we'll give you a multiplier to add to the resultant of these numbers. That handout, you have a copy of this handout, and I believe it has 3 pages with it. Again, just simple, quick reference stuff. Let's show you what happens when we mix some glycol together. In this case, I used 35%. That's a more realistic mix than 50. Okay. So our expansion volume in that case was 0.71. Because of the propylene glycol in that mixture, I used a 1.48 multiplier. So that's going to tell me now this new number is 1.05, not 0.71. And I do the same thing with my tank volume. Watch what happens there. 4.52 times that same multiplier, I'm going to see 6.7 gallon tank required. Okay, that's just to show you how propylene glycol, you start mixing glycol together, your tank's going to get bigger. That's a rule that you can walk away with and understand that. Okay, understand that association. Glycol is going to expand more than water. I'm going to need a bigger expansion tank. Okay, so takeaways from this: location, baby. Make sure you know. Try to get that point of no pressure change at the right spot. Keep it as close to that system pump as you possibly can. Okay. I called out 12 pipe diameters. Okay. Some people I've heard call out 12 inches. So anyway, know how to figure out what that calculation is and how to use it, how to put the numbers together to get the number you're looking for. Acclimate and check the tank's pre-charge pressure or your football. Okay. Just remember, prior to installation, prior to being on the field, make sure it's right. Okay. Reconsider the maximum more realistically, right? That maximum number is what I've kind of harped on. I want you to think about that. Okay. Hey, with expansion tanks, if you're on the edge, man, round up. I think you got that. I pointed that out on the handout, as well as I've said it a couple times now. Just round up. Okay. It's not going to hurt you. And basically that closes these. There's 2 things about an expansion tank. Okay. As far as, the real estate that it takes up. Okay, if depending on what size it is going to eat up some real estate. Okay, and the price that you have to pay for it. Other than those two things, okay, you can't oversize an expansion tank. Okay, so that's it, John. Why don't you take the con and
Yeah, but Rick, I think that's a really important thing to note. There's no downside to oversizing an expansion tank other than price and potentially size.
right.
Just physical size, but there's no downside no downside at all to oversizing. The
Correct.
downside to undersizing, however, would be what?
Well, that relief valve popping.
Yeah, right. You're going to get a wet floor and wonder why, right?
Yeah.
And another thing I always like to point out with expansion tanks is the manufacturers will tell you that the bladder is not airtight. The diaphragm is not airtight. You can lose through the magic of oxygen diffusion. You can lose up to 1 psi annually from the air side of that diaphragm into the water side. So
that's a good point, John.
yeah,
Absolutely.
that 12 psi charge might, after a few years, drop down to 10 or even 9, and now you might have an undersized expansion tank and not even know it. So that's why in our boiler trim kits we have those isolation valves, so you can actually take the expansion tank off and check the pressure periodically. If you go in and do annual clean check and adjust for your customers for a service call, always check the pressure on the expansion tank.
That's right on. Good point.
Yeah. Jim Jakes asked a good question. Is there an ability for students to have a sign-in login for TACO selection tools for use in class only? As far as I know, Rick, there's no sign-in or login required to use the selection tools on our website.
No, not that anyway.
Yeah.
A lot of this is front door stuff. Yeah, you don't need a special sign in. We just, like other manufacturers, we just, it's a gratis thing. We just give it to you and make our industry better, do better designs, sharpen your pencil. And to the best of my knowledge, you can get right in there just as easy as I showed you.
Yeah, right on a computer. And we also have an app that'll have several other tools on it. It does not have the expansion tank tool on it, but it does have pump selection, domestic hot water recirc sizing, etc. So there's an app that you can download from the App Store called let me double check. What's it called? It's called TACO Comfort.
Let me look at my phone.
Let me look at my phone. It's called TACO Comfort. So all you got to do is download that, and you'll have access to that. But yeah, as far as the tools online are concerned, there is it's a big green T. As far as the online tools are concerned, there's no login required for those.
All right.
All right. Excellent. Great. Let's see. What else we have? Stephen Jennings says, I appreciate the seminars that aren't just big sales pitch. You guys rock. Well, Stephen, thank you. As do you. You rock as well.
Absolutely. Thank you.
We definitely appreciate it. Francisco, thank you very much. And excellent. Awesome, folks. And we'll stay on for as long as you guys have questions, but we do appreciate the gift of your time today.
Absolutely.
It's always a pleasure to spend time with you online on these TACO Tuesdays. And again, between Rick and Dave, and Brett and Rich and myself, we've got TACO actually has 5 full-time technical trainers. It's our job to offer these training programs for you, and no one else actually comes close to that. So that's kind of an important commitment we've made to the industry, and we hope it is of value to you, and that this stuff is something you can use in practical applications starting right away. That's our hope anyway. So again, I'll open it up one more time for any other questions you folks might have that we can address for you. If not, just remember, Tom Brady was innocent. The ideal gas law proves that he did not. It's more probable than not that not a doggone thing happened to those footballs. That's all. I'm going to go to my grave believing that. And you just proved it again today for me, Rick.
Glad to help.
There you go. Alrighty, folks. Well, hey, it seems like there's no more questions out there. So again, thank you so much for the gift of your time. We truly appreciate it. And we will see you next week on TACO Tuesday.
All right. Boom.
Bye-bye.
See you later.